also a pleasure to share this session with Louis, with whom we had many discussions. Very nice. So I want to talk about the interplay between pseudogap physics and the Fermi surface topology. And when I think about the pseudogap, I really think about the pseudogap that Louis was talking about in whole-doped Cooper superconductors. The main observables we will be looking at is mainly the spectral function. So in this pseudogap regime, the spectral function shows a suppression of antinodal quasi-particles, while the nodal ones are still more permitted like. So there are many open questions behind the pseudogap. What is the mechanism that drives the pseudogap? What is the role of the Mott insulator here in the parent compound? Is it something very generic that only seen cuprates? So is it something specific to that, or is it more general? Then there are more questions about is it good or bad for superconductivity. So I won't answer all of these questions, but try to address at least some of them. And this is not an experimental talk, so we'll be doing theory on maybe the Hubbard model, which is the simplest model that maybe encapsulates the physics. So this is a work that has a number of collaborators, but the main actors are Wei Bu. He's been mainly interested in understanding that interplay between Fermi surface topology and pseudogap. But we also had to make a number of methodological developments, especially with diagrammatic Monte Carlo. And it's really Fedor Shipkovitz at the Polytechnique with here, Ricardo Rossi, who has been pushing. But then we've also, of course, there's Antoine involved in this work. We've had discussions with Louis. We've been collaborating with the team of Subir Sachdev and especially Michel Ferrero, Eugenia Kozik at King's College. So the Hubbard model we investigated mainly using two techniques, the dynamical cluster approximation and the diagrammatic Monte Carlo. So I'll say a couple of words about it. So dynamical cluster approximation. So this is an extension of the dynamical mean field theory. And again, the idea of the dynamical mean field theory is to start from the lattice Hubbard model. So this is the full original model, and make an approximation where we suppose that the self-energy is local, that it's not a k-dependent quantity. If you assume that, then you can show that you can map the original problem on an Anderson impurity model, and there are good algorithms to solve it. So here the price to pay is that we lose the k-dependence in the self-energy. So there are extensions of the MFT that try to reproduce some k-dependence. One of them is the DCA, the dynamical cluster approximation. And there, the self-energy is patch-wise constant in the Brinois zone. So you have the self-energy takes the same value in those patches, but different values between patches. And the bigger, if you want, the price to pay is to solve a larger number of impurities in your Anderson impurity model. And as you do so, you get a finer and finer resolution, but this is very heavy. So typically we solve 8 sites, sometimes 16 sites for the results that we show. The other approach, and I'll say a bit more about it because we've been working a lot on this, is diagrammatic Monte Carlo. You've heard about it this morning with Nikolai, so I'll repeat some of it. So it's a technique that allows you to look at the model directly on an infinite lattice at equilibrium. So I'll mainly focus at equilibrium here. Then you express a physical observable. It can be the double occupancy, it can be the wind function as a power series in the coupling U here. So from a diagrammatic point of view, you can think, for example, that log Z as a sum of diagrams, and here in this example, it's the sum of all connected vacuum diagrams. So in principle, this is a series. It doesn't need to be convergent everywhere. So generally, it has a finite convergence radius, and this is controlled by the fold structure of the quantity of interest in the complex plane. So for example, if I consider this is density in the atomic limit here as a function of U, and I think of U as a complex number, and I plot this in the complex plane. So 0 is here, and you see these are poles. So typically, those poles will control the region where your series is converged. Now, you need to compute those coefficients. That's the whole game. And there are challenges behind this. There's a side problem, so it's not easy to compute as many of those coefficients as you would like. And even if you do have those coefficients, because of this convergence radius that is finite, sometimes you have to think about how we can go beyond that convergence radius. So there's been work on both these aspects. To be a bit bit the sign problem or to go to have smaller error bars in the computation of the ANs. I mean, originally, the algorithm, the diagrammatic Monte Carlo, as proposed by Nicolai and Boris, was sampling one topology after the other. And so if there was sign alternation between the topologies, that could lead to a larger variance in the computation of the coefficients. The same thing comes with the integral over internal variables over time, for example, that can also be variance. So one of the improvements there was to sum over all topologies at every step. Okay. So in principle, this would come with a factorial cost because there's a factorial number of topologies. But it's been shown, and this is a nice work by Riccardo Rossi, that you can do that in 3 to the power n. It's still quite expensive, but it's not factorial. And so that is been quite a bit of an improvement, and that algorithm is called CGAP. Now, there's been a lot of work by different groups on either different ways to group topologies or better ways to sample or to compute the time integrals. There's also been effort on the real-time versions of those algorithms, but I won't discuss that. Now, the second challenge, and I think we've mainly been focusing on this, is, well, imagine I have my coefficients now. It may be that, imagine I'm in a situation like this. I'm computing the density, and I want to have the result at that value of u. But my code structure is such that I have poles closer to the origin than the actual value when we evaluate the series. And so how do I go beyond that? So there's different approaches. Nicolai mentioned conformal maps. So this is an option. Try to make conformal maps to change the location of the poles and move the evaluation point closer to the origin. One thing that Winston have been doing, we've been playing with the freedom that you have on choosing your starting point to construct your perturbation theory. So there is a bit of freedom in deciding what is your non-interacting propagator in your theory. So the simplest one, and this is the first thing we tried, was to sort of shift, if you want, the chemical potential with an artificial alpha here. And then you need to compensate for that shift in your perturbation theory. So there's more diagrams that you need to take out to compensate for that shift. But in doing so, you change the structure of your function in the complex plane, and you can improve quite a bit. So we try to generalize these ideas more recently to shifts which are both frequency, momentum dependent, but they can be themselves functions of the expansion parameter u. So that makes, if you want a renormalized propagator, that is itself a function of the expansion parameter. And we've shown that you can also do that in exponential time using determinants. So that's something we just put up the archive. And I'll show you in a minute what results we can obtain by doing that. Okay, now I'll turn to results and try to convey a couple of messages that I hope are quite general and are things that I think are more or less established now for the Hubbard. The first thing is that I try to show you that I think we have evidence that there are pseudo-gaps in the Hubbard model. There's different situations, and this is more to give you an idea of what we can do today with diagrammatic Monte Carlo. So this is the half-filled Hubbard model this time, no T prime, just making a nearest neighbor happy. So we can compute, this is the phase diagram in TU, the phase diagram, this is diagrammatic Monte Carlo. And we see there's a crossover between different regions. So starting from the high temperature, I'm in an incoherent high temperature insulating, like if you want, very incoherent regime. Then I enter a Fermi liquid regime with well-defined quasi-particles. And eventually, I get very long range order. The system doesn't order, but the correlation length becomes very long. It opens a pseudo gap, and then you move to a lag regime. And this we can really compute and get the corresponding self-energies using diagrammatic Monte Carlo. So that is a bit the state of the art in the half-filled Hubbard model. This is nevertheless not exactly the point today. I want to really go to the whole doped cuprats. So these are results that we obtained in the whole doped Hubbard model. So this is actually what we obtained 3 years ago with Weibu, using the original diagram C algorithm at that time. And the typical parameters we could have are those here that bring us on this cartoon, I would say just at the very top of the pseudo-gap regime. So that's where we were, but we nevertheless had clear evidences for a nodal antinodal differentiation. So in this one, for example, this is a path in the Brillmore zone. This is the measuring part of the self-energy at the lowest frequency. So that gives you an idea of how much the spectral function will be suppressed. And you see that the suppression will be stronger at 0 pi at the antinode than it is at the node here. By the way, this is a nice comparison between two different techniques, DCA, extrapolated from large clusters, and diagrammatic multi-cloud. The same thing is here. We can also show that the suppression is actually higher at the antinode than at the hotspot. So this is definitely not hotspot. By using the RDADs, this algorithm I was talking about, where we use different starting points for the perturbation theory, we can now push this to lower temperatures, actually twice as low. So that's quite a bit of a challenge. And this is what we see for the spectral functions, which is here. So that's two temperatures. This is the same temperature as the previous slide, and this is the lower temperature. Actually, there's not such a big difference. I think we were expecting to see something bigger, but we definitely see that there is suppression of spectral wave and a pseudo gap in both cases. But not much more is happening here, and we suspect that maybe we're at interaction values of U that are just a bit too low to see something more exciting physics. So we have to pick up the larger value of U. Now, what about the origin of that pseudo gap? So those were diagrammatic Monte Carlo results, and now for the rest of the talk, it will be a lot of DCA 8 sites or 16 sites. So we did a fluctuation diagnostics. This is something that was first done by Ole Gunnarsson and Thomas Schäfer was here on DCA calculations, but we did it with a final case resolution here. And the idea is basically you decompose the contribution to of the self-energy in pieces as a sum over transfer momenta of contributions that you can look at in different channels, either the spin channel, charge channel, or pairing channel. Try to understand what it is that reinforces this. So what we see is that in the charge and the pairing sectors, nothing really special is happening, nor for the nodal or antinodal self-energy. There's really nothing going on there. So the mechanism behind the pseudo gap has definitely nothing to do with charge or pair at those times. Now in the spin sector instead, there's a lot more action. And it's quite different between what happens for the nodal self-energy and for the antinodal self-energy. So for the nodal self-energy, basically the mechanism is incommensurate Fermi surface to Fermi surface scattering, which is very much what you would see in a kind of weak coupling theory, which sort of explains why the self-energy is a lot more Fermi liquid-like at the node. At the antinode instead, most of the contributions are commensurate. As you can see, as you can show, we measured this, that they come from short-range antiferromagnetic correlations. So the correlation length was typically 1.5 Lattice size. Fairly short. Now, to go a bit further, we looked at the self-energy in real frequency here, and you see that the pseudo gap always comes from a pole in the self-energy. This is what's shown here. And that pole is not necessarily at zero frequency. It is sometimes a positive frequency, sometimes a negative frequency, and that we investigated by changing T prime, the next nearest neighbor hopping. So according to the value of T prime that you have, that pole in the self-energy that creates the pseudo gap at the antinode moves from negative energies to positive energies. So it's a different case. So that's what's at the origin of the pseudo gap, but it comes with some consequences. And that you can understand from the Hamiltonian relation here. If I take that and try to compute the contribution of the self-energy, of the real part of the self-energy at low frequency, which is something that controls the shape of the Fermi surface, because this is basically what's going to renormalize your chemical potential. Well, that comes from an integral of that pole, and according to whether the pole is at negative or at positive energies, this contribution here will be positive or negative. So according to the value of T prime, the effect of correlations will be either to make your Fermi surface more hole-like or more electron. And it's a pretty strong effect, as you'll see in a second. Another point that I want to make is that the crossover between weak coupling and strong coupling, if you look at it, for example, as a function of U, so if you look at this renormalization of the Fermi surface as a function of U, it's a very sharp crossover. So that's a plot that illustrates this. So we look, the main curve here to look at is, for example, the blue curve. This is a description of how much your Fermi surface is modified by interaction. So for a big range of values of U, this is actually basically not changing at all. And quite suddenly, here at values about 5, 5.5, very suddenly, there's a very strong effect. So the crossover into the strong coupling regime is a very sharp. Now, there's definitely something going on here with the pseudo gap and that pole in the self energy, which is renormalizing the Fermi surface. So I want to understand a bit better what's the link between those two things and connect to what Louis was talking about earlier. I'll spend some time trying to explain that figure a bit more in detail. So we did an analysis here of the phase diagram as a function of t prime, different values of the next nearest neighbor hopping, and the whole doping. So if I think about a non-interacting system, there are regions in this phase diagram where the Fermi, the non-interacting Fermi surface is whole light, and others where it's electron light. And that is that dotted line here. Below that line, the Fermi, the non-interacting Fermi surface is whole light, and above that line, it is electron light. That is without interaction. Now, we introduce interaction in the system, and the first thing we see is that that dotted line here is very renormalized. It becomes that blue line here. So it has a very strong effect, especially here at small doping. It's a very serious effect. So you're displacing the Lifshitz transition of the Fermi surface from whole light to electron light to much larger values of the doping. That's the first thing. The next thing we looked at on this phase diagram is where the system has a pseudo gap. And that is that black line here, which exactly merges at some doping here a bit below 15% into the blue line. So below that black line, the system has a pseudo gap. On that side, it does. So there is a big region where the existence of a pseudo gap and the change of the Fermi surface from whole light to electron light are concomitant. And there is nowhere on this phase diagram a place where the Fermi surface is electron light and there is a pseudo gap. I think this is compatible with what is seen in experiments. Now, everything here is driven by that red line that I'll try to explain now. So that red line on that phase diagram is the moment when that pole that I was talking about earlier in the self energy goes through zero. So that's work on the self energy, it's most singular at zero frequency. So that's that red line here. Above the red line, the pole is at positive energies here, for example, and the renormalization of the Fermi surface is such that you push away the Lifshitz transition. But it's also the same pole that introduces the pseudo gap. And so it is that pole that drives both effects. At the same time, it gives you a pseudo gap, and at the same time, it pushes the Lifshitz transition. And because everything is so sharp, the crossover between weak coupling and strong coupling seems to be so sharp, the moment you lose the pseudo gap, you also lose the renormalization of the Fermi surface, and both effects take place. I'd say that's our understanding of what's going on there. Now, we want to understand this a bit better. So it seems there's a connection between the Lifshitz transition and the pseudo gap. And at the moment you go through a Lifshitz transition, your Fermi surface exactly goes through the Van Gogh singularity in the square. So we wanted to understand if this is something generic, if we go to other models. So we investigated a number of other models, but here I'll mainly show results for a modified sort of triangular lattice model. So we consider a triangular lattice with a flux. So your hoppings are complex hoppings with a flux here, so that you pick up a flux phi here as you go along one of those triangles. What's interesting about that model is that when you tune the flux, you change the dispersion, so you change your Fermi surface, but you're not changing, at least at second order, the magnetic correlation in your system. So if you take the large U limit, the J, if you want, that you get, the simple sort of effective Heisenberg model, is the same. Now, what happens to the pseudo gap in this system? So different values of the flux. So these are two examples for the flux. This is the triangular lattice in the absence of flux. A very small hole doping, so that's 2% hole doping. And we see that these are the self energies here as a function of Matsubar frequency, and they're all Fermi liquid-like, or at least there's no evidence for a pseudo gap there. So this is a system you really have to go to extremely low doping before you see anything happening. So there's, a priori, I would say, no pseudo gap in this system as you lower the doping. So these different curves are for 8% hole doping, 4%. If you do the same thing for a flux 3 pi over 4, the situation is completely different. At 8% doping, you're still firmly liquidish here, but very rapidly, as you lower doping, you have an insulating self energy. And if you look at the cycle function, you start seeing a dip here, which was not at all present. So there's definitely something going on as you change the flux or your dispersion or your non-interacting surface. So we found something. Oh, the formula is here. Doesn't matter too much. It's the same as this one, in which you just put a K. So what changes as you change the flux is the location, among other things, is the location of the Van Hoff singularity. So from flux 0, the Van Hoff singularity in the Brillouin zone is here. If you change the flux to 3 pi over 4, it moves here. And what we observe, and this is, I would say, empirical, we don't have a clear explanation for it now, is that if I look at the surface, which is defined by the equation epsilon of k, this is the dispersion, minus mu, plus a Hartree shift equal to 0. So this is defining, if you want a modified Fermi surface, a Hartree shifted Fermi surface. These are the black lines here and here. And it turns out that when those lines go through the Van Hoff singularity, there is an enhancement of the pseudo gap. If it's far from the Van Hoff singularity, we don't see a pseudo gap. And this, so that basically is sort of an equation that tells you, will I have an enhancement of the pseudo? And we did this for many different models. So this same equation holds for the square lattice. It holds for a modified square lattice with asymmetric hoppings. We tried it in many different cases, and that always seemed to be a good criteria to decide whether you have or not a pseudo. But it still lacks a complete explanation. That's for now just say an explanation, but definitely seems that the Van Hoff singularity is the key player, even though this is not at all weak coupling physics, the correlation length is short. Okay. So to conclude, we try to understand a bit the pseudo gap and what it would be the recipe to get a pseudo gap. The first thing to understand is that it seems that the fermiology of an non-interacting system is important. It seems you need at least 3 ingredients. You need antiferromagnetic correlations, short range. How short is something that I think would be interesting to understand better. It looks like having a Van Hoff singularity is something that definitely can enhance the suppression of fuzzy particles. And we have that criteria that seems to tell you whether or not you're going to have a pseudo gap. Actually, I should have added maybe one more point, which you also need to understand. In some situations, it seems like unclap physics seems to be important, but this is something which we need to understand. But again, this is not weak coupling physics. It's tempting to say, but look, this is very much like weak coupling physics. But the correlation lengths are extremely short, so we're not at all in kind of the physics that you have when you have long range and magnetic almost order. And there's no examples where we saw a pseudo gap in the absence of the Van Hoff singularity. So definitely to make progress, I think having a finer K resolution would be very important to understand how exactly those things are connected. From the diagrammatic Monte Carlo point of view, there's many things we're working on in that direction. Like Nikolai was saying, we're more and more able to go and investigate broken symmetry phases. These are some very recent results by a student at the Medical Polytechnic, showing how the magnetization goes to 0. This is in a 3-dimensional Hubbard model, so this is something new that was not possible before. We also investigated better starting points. So for example, in the half-field Hubbard model, if we wanted to compute double occupancy until a couple of months ago, the best we could do is compute things up to u equal 2 or 3. Now we can go all the way to u about 13 by using a better starting point, which breaks the symmetry and somehow encapsulates the fact that your system has almost fuzzy long range order. At a broader perspective, because diagrammatic Monte Carlo is one method, there's many other methods to look at the Hubbard model. I think there are a bit 2 classes of I would say algorithms, some that are more wave function algorithms that start from 0 temperature and go bottom to top. Some others more like the MFTN extensions, which rather start from high temperature and go down. And there are more and more efforts to try to shake hands between these methods, to benchmark them, to compare them. There were some examples, this nice work of James Leblanc and many others. And there's another effort which is starting just now, led by Thomas Schaefer, who's here, where we really go look at the Hatfield-Hubbard model at U2 and investigate how things change as a function of temperature, looking at a whole set of methods. This is just to give you an idea. And this, I think, is a very useful thing to do, to be able to have an idea of what are the strengths and weaknesses of methods and how they can be complementary. So hopefully this was something that you could have seen in that. And with that, I would like to thank you. I would say no. I don't think we've seen that. Even though maybe if we really push, maybe on LMI have an idea. If we really went electron doped and started from a positive T-prime model, and the moment, if your Fermi surface there was just touching the antiferromagnetic zone, maybe we'd have an almost node of pseudo-gap line.
Can you repeat the question?
Oh, yeah.
Who may be connected.
Yeah, sorry. So the question was, do we ever see a pseudo-gap at the node? The question, I think there are calculations, some done by Marie, where this is seen. In doped LSCO, I would say no. I mean, that, yeah, I would say in that situation, I don't think we would ever see that in our this is not something we're seeing in our application. Sorry, say it again. This one? What is defining those two lines there? Yeah, so this is a criteria which is taken from, you look at the self-energy in Matsubar frequencies, and you look at the last points you have for your self-energy, and I think the criteria that Fedor will confirm is the slope there. But no, I mean, what it basically means there is you start having coherent quasi-particles. Before that, your self-energy looks very insulating, like your system is a vegetable, there's nothing going on there. And progressively, as you lower temperature, you just get a more coherent system, and your self-energy looks more Fermi liquid like that. There's nothing more than that there. Yeah, well, it's a crossover, obviously, but yeah, somewhere, yes. So that's really the incoherent to coherent. Now, it depends exactly what you mean by Fermi liquid. If your definition of Fermi liquid is having a quadratic self-energy, this is definitely not the temperature we're talking about. Here, I'm talking about coherent quasi-particles. That's really what I mean. Yeah. Yeah.
Oh, okay. So I actually must have missed this. So by pseudo-gap, you mean basically a meaningful fraction of single particle density states at the end node?
Yes.
So, and this is not a distinction, but if you wanted to talk about a gap versus wanted to talk about a smearing, like a scattering rate, these calculations do not distinguish those two narratives about what.
So are you asking whether we see the difference between a true gap and a pseudo gap?
Well, I'm asking more about a pseudo gap versus a strong scattering, large line widths, right? You have low density of states because of a broadening of the line of the resonance, or you could have it clearing out spectrally towards higher.
Yeah, I think that's more what we're seeing because we are really looking at the self-energy. So what we see is an increase in the self-energy and the corresponding scattering rate.
But just to clarify, if I understand you correctly, the distinction that you were drawing is between a spectral function that is many body density state, which more or less stays constant and then tends to decrease as you go to higher energy, albeit starting from a low value, or a spectral function which starts out low and increases as you go away from the central spectrum. Is that what you're asking? Which of those two things does he see?
Yes.
Great. Okay. Which of those two things do you see?
So sorry, you have to rephrase it.
Okay. There's two scenarios for a spectral function that starts out small and is just broad and then decreases as you go away from zero frequency, or a spectral function that starts out small and then increases as you go away from zero frequency.
Well, it does increase.
That's the question. Which of those two things are you
it
describing?
increases as I move.
Okay.
But the latter. And it's always
That's a real
it's always
thing.
yeah. But it's because of sigma double prime.
It is.
Scattering rate. Yes.
No. It's because there's a polling signal.
Yes.
That's not a scattering. But
Yeah.
Okay, fair enough.
The imaginary part is becoming.
No, okay, yeah.
Yes, but there are those sort of polling.
There's definitely, yeah.
It's small.
How is your statement with the these are all smaller than double prime or other mediums?
Sorry, I'd have to.
Can you actually give this example? What you already saw in another talk, and it's always the low
Yes.
or the pseudo gap is yes.
Yes.
This is affected by the double prime.
Oh, if we put a T double prime there. Okay, I have to confess there we have never done a very systematic study there as a function of T double prime. So this value. We've done systematic studies as a function of both T prime and T double prime to see when we have a maximum pseudo gap and what's the criterion for this. In the last part, but we do not have that same plot for values of T double prime, even though I suspect the results would be. I don't think
At least in cluster propagation theory, there's pseudo gap at the second case.
yeah, I don't think this would fit, but we haven't actually.
As far as we know, the Italian rate does not have a crossover from a whole-like to a Fermi-like feminist. Would you be ready to think there is no pseudo gap in this material? No, the inequality is still whole.
Yeah.
So no problem. You would also expect it. You just expect the pseudo gap to happen at the lower. Yeah. If you can make the sample.
If you can make the sample, in principle, you can actually see.
No, wait, but I think that your statement is that suppose that in the thallium compound, the Fermi surface always stays electron-like.
Oh, if it remains.
No. His statement, whole life, sorry. If the Fermi surface always stays whole life, no pseudo gap.
No.
That's the question.
So I think it's the other way around. I think the question is whether if it remained electron-like everywhere, whether we would see a pseudo gap. Is that your question?
No. Whole life. I mean, we know from the experiment that the Fermi surface is always whole life.
Yes.
It's
Which
like
means that there's no Van Hoek nearby.
it's like
Yeah,
being at
but you see-
minus 0.4 on this axis.
Yeah, you see, it is not because you're whole like that you do have a pseudo gap. It goes the other way around. You never see a pseudo gap on an electron-like Fermi surface, but it doesn't mean that you always see one on a whole like Fermi surface. So, for example, if you go to those values of T prime here, which are very negative, in this region here, you don't have a pseudo gap, right? But you're whole like nevertheless. Like that. Okay? Like that, exactly. Which has a fairly negative value.
And so it follows from that it is likely that if you generate very underdosed samples
Exactly.
of
You
thallium,
will eventually
which we-
cross that
you
black
will
line
find
and see a
some
switch.
Okay, this will be the last question.
Oh.
Go ahead.
Is this open discussion time?
No, we don't have any budgeted until 7 o'clock, so just answer your question.
Oh,
That was your discussion.
well, okay. It's because it's both of you guys. It's specifically about the Stalin business. If you look at that change of P1 plus P, it's not abrupt. It's over a broad region. It's certainly
And so, and here, I mean, it is linking things to the, you know, you'd expect this to be abrupt. That's what I'm getting from both of you. And just to stir the pot up a little bit more, you know, on bismuth 2212, at 19% doping, the pseudo gap's gone, and the Fermi surface hasn't crossed through until at around 30%.
Yeah, again, this is
And what are the things with some disturbing things?
Yeah, well, I think we're basically repeating what you said. We can be at we can be here at the values of P prime, which are fairly negative, and then as a function of doping, here, I mean, the disappearance of the pseudo gap here, I'm not sure it's something very strong. I mean, it will slowly disappear, and you'll end up here in a place where you don't have a pseudo gap, and eventually you'll have your transition here. So I don't expect
Necessary,
necessarily.
not sufficient condition.
Exactly, it's a necessary.
Yeah, I think on your conclusion, that's what you said. But
Okay, sorry.
we can
that was-
turn it around then and say, can we ever see a pseudo gap where there is that the Van Hove hasn't gone through? And we know, you know, if you ask that as a purely theoretical question, yes, negative U Hubbard has pseudo gap all over the place. So, which is
Okay, sure. This is a positive view study. No. I mean, this is, of course, this is a normal state here. I mean, not taking.
So what I'm asking is this thing abrupt? And are you know, is it really something where the Van Hove is controlling everything?
I think at least in that region, I would say yes. I mean, here everything is quite abrupt. If you go to values of P prime that are here, then things are not that abrupt.
Do you mind if we wait for the big discussion?
Yes.
Okay, thank you very much.